In part two of this talk, I introduced a new model of orthographic input coding, the sequence predictor model, or SPM, and I showed that it could do a very good job of explaining data from the form priming project, or FPP, as we see here. And that's promising, but a skeptic might reasonably point out that post-dicting the data from the FPP is not quite the same as making testable predictions that are subsequently confirmed. And this model does make some interesting predictions regarding the costs of reversing letter strings, the impact of shifting single letters, and so on. So for that reason, it seemed like a good idea to run a new experiment in the same vein as the original form priming project. And the design of this experiment is exactly the same as in the FPP. And so in a bold imaginative leap, I'm referring to this experiment as FPP2. And here's the list of researchers who are collaborating to collect data for this experiment. So each of these people will be co-authors on the paper describing this new mega experiment. This list doesn't include quite a few other researchers who will be participating in the sequel, FPP3, which I shall mention momentarily. Now, this is still work in progress, but we already have data from over 1,000 participants. And I anticipate that the final sample will be around 1,200 participants. And here are the prime conditions that we're testing this time around. In the original FPP, the unrelated baseline condition had 6 letters, and it seemed like a good idea to add some unrelated conditions of different lengths, potentially to serve as baselines for other different length conditions, but also because this provides a straightforward test of the impact of the number of incompatible letters, the number of these D letters. 10 of the conditions in this experiment were identical to those we tested in the original FPP. And the rationale for that was to check that it would be feasible to integrate these two experiments into one large database. And reassuringly, it turns out that the correlation in the means for these overlapping conditions is 0.98. We included another group of primes that were designed to test different forms of misordering, most dramatically in the case of a completely reversed letter string. We also had conditions in which a single letter is shifted 2, 4, or 5 positions. We also took the opportunity to see whether the cost of incompatible letters is reduced if those different letters form an affix, or perhaps we should say a pseudo-affix, either a prefix, that's indicated by the PP, or a suffix, which is the SS. And given results in the literature suggesting early morphological processing in mask priming, we might expect greater priming in these two morphological conditions than in their respective controls. And finally, we have some subset conditions which allow us to get at some issues relating to contiguity and the importance of initial letters. So here are the results so far. I'll briefly mention a few of the interesting and perhaps surprising aspects of the data. The unrelated conditions are all clustered down here, where we'd expect to find them, with the ordering 4, 5, 6 letters, and then the mismatch cost appears to asymptote after 7 different letters. But within this cluster, we see 2 conditions that are composed entirely of matching letters. Matching, but not contiguous matching. And in particular, the condition in which we reverse the target leads to priming that's slightly negative relative to the baseline of the same length. And that shows that the misordering cost is at least as strong as the mismatch cost. And in many respects, I think this is a rather counterintuitive result and a powerful confirmation of the sequence predictor model. Now, on the other hand, this result is also entirely consistent with an open bigram model. However, this condition, the BGT, which stands for bigram test, is one that open biogram models predict should be a very effective prime. Now, I expected that it wouldn't be an effective prime, but I didn't anticipate just how bad it would turn out to be. So to accommodate that result in the sequence predictor model, I introduced a new assumption, or modified an assumption, to say that receivers send inhibition not only to preceding letter receivers, but also to themselves. So as well as the misordering cost in this example, there is a cost of the repetition of the letter 4 in 425436. And that's an assumption that will need to be tested with new conditions. Now, I had thought the model might require adjustment to capture early morphological processing, but it turns out that's not necessary. We don't see any benefits of pseudo-prefixes or pseudo-suffixes. Now, here's something of a surprise. I didn't anticipate how good a prime 2, 3, 4, 5, 6 would turn out to be. We hear a lot about the importance of initial letters, but it turns out you can delete the initial letter and have a prime that is more effective than deleting a letter in any other position, and almost as effective as an identity prime. So to accommodate that result, I'm introducing another new assumption, which is that the presence of letters 2 through 6 is sufficient to generate top-down feedback supporting the first letter receiver. And that may not be sufficient to fill in the first letter, but it does allow that receiver to predict the next letter, thereby allowing an illusory contiguity benefit for the letter in position 2. So in this graph, I've combined all the priming conditions from the original FPP and this new experiment, FPP2. And as you can see, the sequence predictor model, with the same parameters as before, although admittedly with a couple of new assumptions, is doing an extremely good job of capturing the data. The correlation is 0.990. And in those conditions where the model slightly overestimates the observed priming, I think I can explain what's going on, but I shall save that for another talk. So the model's doing very well. Now, given the success of this model, it's reasonable to ask whether we might perhaps have cracked the code. I'm somewhat optimistic about this, but I think it would be premature to declare the case closed. Although the model made lots of successful predictions in the new data set, we did also discover conditions where it got it wrong, where I had to invoke additional assumptions to capture the data. So in view of that, we need another experiment. And I'm hoping that for this next experiment, researchers will be able to look at the predictions of this new model very carefully and perhaps identify predictions that they think are problematic or interesting in some way. And we can then take a vote on which conditions we will test in the new experiment. So if anyone listening would like to be involved in that test, please do get in touch with me. Now, if it turns out that we have cracked the code, then that would be good news for a number of reasons. I think a better understanding of the front end of visual word identification will allow us some purchase on some problems further downstream in reading. It won't mean that there's nothing further to learn from masked form priming, and that's something that can be discussed in another talk perhaps. But I'd like to end by considering some implications. One question we might ask is, why hasn't this model been proposed already? Although I've omitted some of the details here, this is essentially a very simple model. And one important reason, I think, relates to the available data. It's just much easier to find this solution now that we have precise data for a large set of priming conditions. But another reason might be that perhaps we've been thinking about this problem in slightly the wrong way. Although there's a certain romantic appeal to the notion of cracking the code, I'm not sure that this is the right metaphor. It encourages us to think about what kind of code or representation could succeed in capturing both item and position information in just the right way. But perhaps the solution to this particular binding problem is to realize that actually there is no binding going on. And it's not position that's important, it's order. And there's an easy way to communicate the order of items by transforming a parallel input into a temporal sequence. Now, that proposal is one that I suspect many researchers will dislike or be uncomfortable about. And it may be possible to develop a parallel account that incorporates the critical features of the matching algorithm I've described. But I think it's not so easy to see how you would explain the features of such a model, and in particular, the mechanism that gives rise to the misordering cost, which I've described in terms of backwards inhibition. Now, perhaps the notion of letter receivers sending inhibition to preceding letter receivers may seem a bit arcane, it's a little bit unorthodox, but I think it has a logical interpretation, because such a circuit would be a useful way to prevent perseveration if you were trying to produce sequences. So I think it's not too fanciful to suggest that the reason the sequence recognition circuit has the form proposed here is because it doubles as a sequence production circuit. So that top-down signal to the first letter receiver that I mentioned would be sufficient to get the full set of receivers to fire in the right order. So perhaps we use exactly the same circuit for spelling a word as for recognizing it in print. And once we start thinking along those lines, it's natural to contemplate the connection to other processes that are more obviously serial in nature. Things like speech perception and production and serial recall, perhaps. And exploring these connections might be a fertile ground for future research.